All right. Can everyone on Zoom hear me fine?
Yeah.
Great. All right. All right. So let's start. Any issues with the last assignment? Any problems which anyone wants to talk about? No? All right, good. Are we like on track to understanding what supervised learning is? Last time we spoke about logistic regression. Was it understandable enough? Any confusions over there? No. Okay. Right. So, but then let's start with the third part of machine learning. So as we discussed the last time, for us to focus on machine learning, there would be 4 lectures on machine learning. We have done a deep dive into different kinds of machine learning algorithms. Sorry, an overview of different kind of machine learning algorithms. And now we're looking at different specific algorithms. Last time we discussed logistic regression, and today we're going to do naive Bayes. Before we do that, did anyone, I know you were there, did anyone join this Oftenly AI webinar? Did you have an opportunity to sign up? No? Okay, no problem. I mean, it's fine if you didn't have the time. They publish, so this Oftenly AI is like it happens every few months that they invite people from different Oftenly companies and they talk about their AI projects which they are working with. And in those AI projects, so in this one, it was Nav and Ruther who was talking about their projects. So I can send you a link afterwards. They have they make a recording and then they upload it on. I think either it's Digdeer website, digdeer.no. You can find over there, but I'll share it with you afterwards. It's nice for you to get an idea on how different, often the companies are working with AI in their environments. But okay. So today we will talk about naive Bayes classification algorithm. Have you heard of this algorithm before? Has anyone heard of this one? Like just heard of it? Someone mentioned it, no? Okay. It's not a conversation you're going to have with your friends. So what really is a naive Bayes algorithm? It's a pretty cool algorithm. It's a very strong algorithm. In the previous examples, we were talking about classifying a cat or a dog, right? So we used to train our model based on the data we provided the model. We trained the model with a preset label data, and then we told it that this is either a cat or that's dog. But what if you do not have that kind of data, and the only thing you can train the model, like when you are training the model, you're giving like a feature set, right? You're telling them since it's a cat and a dog, the attributes or the features you would define is that it has what's the difference between cat and a dog? A cat has more fur, right? They still have 4 legs, 1 tail. What really the difference between cat and a dog? Now that I think about it. Can anyone highlight any difference between cat and a dog? I know cat has more fur than dog, right? But physically, if you see it, the nose is probably different between the two. Yeah. Eyes are, yeah, the eyes, yes, exactly. The thing inside the eye. That's different. The ears are also very different between the two. So when you train the model, you define these feature sets. You would define feature sets like the eyes, the ears, the way they stand. It's also very different the way they stand.
Cats
So these are
also
the
have,
features.
I was going to say the cats also have retractable claws.
Yeah, yeah. So the comment I received from the Zoom is that a cat also has retractable claws. Thank you for saying that. So these are the, yeah, now that you think about it, there are quite a lot of differences between the two. So when you create the model, you define these features and you're like, hey, we think these are the feature sets. This is how you differentiate between the two. But what if you cannot define those features? Like now I'm having problems defining difference between cat and dog. So what this naive Bayes algorithm does, it kind of tries to detect, classify values inside a data set based on the features which are not related to the other one. So for example, if it will consider a dog as a dog because it has 4 legs and 1 tail, but it will also consider a cat as a dog because it also has 4 legs and 1 tail. In our opinion, that should be a different kind of feature set. It should either be an animal or a person. That's the feature set, right? But a naive Bayes does not consider the relationships between the features. And that's a very important thing. In logistic regression, the features were related to each other. Features were kind of dependent. Here, the features are not related to each other at all. And okay, before I explain to you what this mathematical formula is, let's take a look at another example. One second. This goes, yeah. So let's assume we have this data set in front of you. You have a data set of fruits, which is, you have like 3 features on it. You have features like the fruit itself is a banana, orange, or something else. And the features are that it's long. How long would it be? How sweet it would be? And does it have a color, yellow or not? And you have given different weight based on different fruit. So for banana, you have given it a high score of 400. And I mean, that's just the data set you have, right? It can be any kind of data set. It could be a weight, it could be the quantity itself. So you have like 1,000 fruits and 400 of them are bananas. 400 of them are bananas which are long. 350 of those bananas are sweet. 450 of those bananas are yellow, right? But in total, you have 500 bananas. But every banana is not really following the same category. Some bananas are green. They might not be yellow. And the same goes for orange, and the same goes for other as well. So you classify everything based on the information you have in front of you. And what you do is, yeah, if you just do a simple statistical evaluation of the data set you have, you don't have to do some math on it. You see, like, you have a total of 1,000 fruits, right? And 500 of them are bananas. It's very obvious that 50% of the data set is bananas. Then since it's 300 oranges, then percentage-wise, 30% are oranges and 20% are other fruits. So so if we apply more statistical formulas on it or try to get more information outside our data set, we can say that from 500 bananas, 400 are long. So in mathematical calculation, that would be 0.8. And then 0.7 are sweet and 0.9 are yellow. And the same goes for oranges and the same goes for remaining fruits. Right? Now you have these numbers in front of you. You have a good idea of how much percentage or how much value of bananas are long, are sweet, are yellow, same for oranges and the same for everything else. And now you want to find associations between them. So what you do is you take the same formula I showed you before, the bias theorem, and you try to, what you are trying to see is you're trying to predict the class. So if you use this formula and you try to give it all the information you have, but then you're trying to predict if a new fruit which comes in, does it belong to a banana? Does it belong to the class of orange, or does it belong to any other class? So this is the kind of mathematical calculation which will be happen in your algorithm. So the same values which we picked from the previous data, those were 0.8, 0.7, 0.9, 0.5, you will apply over here. And if you jump down to number 2, that's where you're trying to predict if it's orange or not. That's the formula which I showed you in the previous screen, which was actually this one. So what we are trying to show in a bias theorem is the probability of an event which will occur based on the history of which already has occurred before. So this formula is the one applied here. It's the same formula, right? You use it for banana, you use it for orange, and you use it for fruit as well. So, I mean, what you get when you try to predict one class based on the information you have, you again can get a value which is more of a percentage score, and that score will tell how close it is to predicting if that is that specific class or not. Yeah. Another example to show that would be text processing, like natural language processing. So in a natural language processing, the way natural language processing works is, do you know what natural language processing is? Do you want me to, is there anyone who wants me to tell what NLP is? Okay, I'll just give a brief short introduction of NLP. So natural language processing is a branch of machine learning and AI. What we do is, like, in machine learning itself, we try to predict values which will be for numerical values, or we will try to predict statistical values. We mostly work with textual data, we work with images. So that everything you do with images, everything you do with text, everything you do with binary, that would be machine learning, deep learning. But when it comes to language itself, when it comes to English, Norwegian, Swedish, then, and you use AI on it, then it's natural language processing. So everything around language would belong to the branch of AI which is called natural language processing. And everything with images, text as in numerical value would be machine learning, deep learning itself. So when we but I mean, these are concepts, right? You have machine learning, deep learning, and you have natural language processing. But underlying, if you look at the algorithms they use, they're more or less the same algorithms which are being used for to solve different kind of problems. So if when the same algorithm, naive Bayes, works for natural language processing, and we're trying to, let's suppose we're trying to detect the mood of the person. We want to see, we have a huge text of information. For example, you just uploaded the chat. You've been chatting with your friend, and you have a history of that information, and you put it to the natural language processing engine, and you want to see how angry or how happy you were in that conversation, and you want the algorithm to actually predict how happy or how sad you were. So what? And let's suppose you were using naive Bayes algorithm. So the way that algorithm will work is that it will try to detect, it will look at the text, and it will try to detect the mood of what you were saying in it. And it's another thing to identify how the mood comes in. So I'll talk about how you associate the mood with the text itself. But for every, so first what it does, it like if you have a text which says I am very angry, and you specify that if the text says I'm angry, this specifies as a mood. And if there's another text which says like I'm a superstar, that would be I feel like a superstar, that's also a mood. But if you're saying like it's going to rain, that's not really a mood, that's not a mood, that's just that's a sentence. So again, you have to label these categories before, and then based on these categories, it will just read through all the text, and then it will count the occurrences of the mood category and the occurrences for the ones which are not mood category. So in a sentence, it has more than a specified threshold of mood occurrences. It will then flag that you're probably feeling sad or you're probably feeling happy. The other way this is done is that, for example, when we try to detect hate speech, or we try to detect if people are, I mean, that's the same branch of sentiment analysis, right? You want to first you want to identify how angry or how happy people are, but you also want to see if people are abusing other people or saying some bad things over the internet, in chat or in Twitter forums or something like that. So what people do is that they download a dictionary of huge words, which would be bad words. So every language has it, right? Every language has its own history of words, and there's a huge database of those words. So what they do is they download then all this dictionary of words, which is already classified as bad, good, bad, or good. And when you have it, you just train your model with this labeled data, and you tell it like, we know these words are wrong and these words are right, and based on this data, what do you think how this conversation was going? The algorithm then says like, we think this was bad or this was right. And that's how they try to detect hate speech on Facebook, on Twitter, or even the way Ruther is doing that. We do our sentiment analysis. Any confusions regarding Naive-Bayes algorithm? Because we are done with that algorithm now, so we're gonna jump over to another one. Any questions? Yeah.
Based on previous data, you see open it is long and then the first stance of the team.
I don't think I follow your question, but that's also because we didn't use distance between us. Could you please repeat it?
I was with you,
Right. That's just the data set, right? Yeah. But if you get an answer you're looking for, yeah, all objects, right? Okay, so the next algorithm in classification machine learning would be support vector machines. Now, I mean, the most important thing about a support vector machine is that it tries to classify the data by creating a lot of how would I say it? Hyperplanes. So a hyperplane is a line, right? A hyperplane is just a line which kind of it tries to draw as many hyperlanes as possible. Hyperlane is a line which distinguishes one set of data, one class of data from the other class of data. as far as possible. So in this example, in this diagram, the green lines are hyperplanes. There are almost 1, 2, 3, 4, 5 hyperplanes. And these hyperplanes are drawn based on each object being furthest away from the other object. So I mean, these three objects, these three square boxes down here. Oh, I should do some else. So these three boxes over here, right? When you look at these three boxes, there's no need to draw a hyperplane on this kind of data set. Just because it's so far away, it kind of knows that all these three belong in the same classification of data. But the problem is actually this data set. That's always a problem, because when you classify a data set, or when the algorithm classifies a data, it's very easy to classify data which is furthest away. But the more the data set comes closer to each other, that's where it becomes more problematic. And that's why we switch between different algorithms as well, because that's the hardest data set to work with. So what support vector machine does is it tries to draw like a line specifying how far each data points on, for example, this object and that object is. And when you draw a line between these two objects which are furthest away, it tries to draw as many lines as possible. And when it has done that, it then jumps on to this diagram, which is trying to find the optimal hyperplane. And that would be one. So first it tries to draw as many lines as possible. And based on those lines, it then identifies how far the data sets are. And then it finds the maximum margin and the minimum margin. And that's the ideal hyperplane it can use to identify how the data set should be classified. This is very useful, because if you have a data set which is overlapping, same example as a cat and a dog, where you have similar attributes, but you know data is very different, then you would use support vector machine, because it will automatically classify data for you. Yeah. Just a bit more on hyperplanes, because hyperplanes are used a bit more in a lot more algorithms as well. So you can you normally use a two-dimensional hyperplane, which is that one, but you can also use a three-dimensional hyperplane. There are more n-dimensional hyperplanes, but depends on how many features you have. So you can, depending on how many features you have, you can have that many types of hyperplanes. One reason why hyperplanes are useful is that they can find a lot of complex relationships between your data without you having actually to do all these things on your own. So if you have a data which has a lot of complex interdependence relationship, and there are hundreds or thousands of features, there are data sets who have thousands of features, then perhaps it's better to use a support vector machine, because it can automatically detect those relationships. Support vector machine is used a lot to detect cancer inside the cells. It's used to predict the driving route, how the driverless car will go around, face detection, image detection, and handwriting. So yeah. So I mean, the pros are for sure. We spoke about being the multiple feature thing. Yeah. So number two is very important. Like if you have if your features are quite a lot, then quite a lot. How would you define quite a lot? As a rule of thumb, if you have more than 10 features, then it's advisable to use support vector machine because it works in much better way if you have more features. It's also said to be more memory efficient. So yeah, that's a pro. Yeah, there are two cons mentioned over here. I haven't tried these cons, but it says that if you train the model on your data, it will take the training time is quite long. And that's because, I mean, if it's trying to find based on all the feature sets you have defined, if it's a two-dimensional feature set, it's no problem. But if you have an n-dimensional and the features you have like 100, and for every 100 kind of features, it will try to classify the data based on those features. So it takes more time to classify it. So if you have a data set which is 1,000 entries, all right, it might take a few minutes to do this. But if you have a data set which is based on million entries, then it might take a few hours to actually train that algorithm on that data set. So just because you are giving model the job of classifying the data set, then the model will take time to actually train itself. And since it's doing the classification, it will not give you like a probability estimate, which logistic regression was doing earlier for you. So there are so what we have done now, we have discussed three classification algorithms. One, we discussed logistic regression, we discussed naive Bayes, and we discussed the third one, which was just now support vector machine. So there are other classification algorithms. We have decision trees, k nearest neighbor, random forest. But I mean, I will leave it up to you to read them at your own time. Random forest is very interesting. A lot of people use random forest. It's like if you're starting with machine learning, random forest is like well known for a lot of use cases. But try them out. So I'm not going to cover them in this class today, but I leave it to you to just explore it in your own time. We will now jump on to regression kind of algorithms. Now, as we showed earlier, that when you talk about supervised machine learning, there are two kinds of supervised machine learning. You have classification algorithm and regression algorithm. So now we're done with the classification type and we'll talk about regression algorithm. And in regression, we'll only talk about two of them. So then when you're done with regression, then we're done with supervised learning. Then we'll talk about non-supervised learning and then reinforcement learning and recommendation systems. So yeah, but before I begin with regression, can we take a break? It's 3:05, so we meet in like 25 minutes. Yeah. Okay. So let's start. Regression. Yeah. So regression algorithms, what are regression algorithms? Regression algorithms are those algorithms which are used to detect a continuous value. So previously we were doing classification, right? We were like, if this is a cat or a dog, but if you want to predict a continuous value would be predicting the price of a stock, price of a house. If you want to predict the weather, what degree of the weather would be tomorrow, that's also a continuous value. So regression always applies to a continuous value. Classification only applies to how you classify the different data sets. And another example would be like if you want to predict the income of a company based on previous information. And this is also continuous value, right? It's changing over the years, and then you're going to predict something which doesn't exist now. So of course, when it comes to, or no, I should not, well, yeah, okay. When it comes to stock market, and you want to predict the price of a stock, you would use regression algorithm there. So then okay, so let's do this. So I'm going to ask you a few things. I'm going to give you a few ideas, and then I'm just wondering if you could specify if it's a classification algorithm or a regression algorithm. Do you know what churn is? A churn is a business concept which says like a company like Telia, for example, or Telenor. Telenor has like 10,000 users. They have more than that, but let's assume they have 10,000 users. And 50 of those users leave the company. So that's churn. So if Telenor is trying to, that concept is called churn. How many people, how many users have canceled their subscription and going somewhere else? So every company needs to calculate the churn. And that's how they need to know, like, all right, we had 100 signups, but we also had 50 who left our service. It's very important to know. So if you are calculating, if you are trying to make an algorithm and you want to predict customer churn, you want to see if a customer will leave or not, what kind of algorithm would you need? Would you use? Would it be a classification or a regression algorithm? Yeah. Yes. 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 So what would that be then? Sorry. So what I'm saying is like, yes, if you were to specify the customer as a binary value, right? And you want to see if the customer would leave or not, then what in that example, would you use a classification algorithm or a regression algorithm? Correct. Yeah. 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 Exactly. Yeah. Yeah. The question is, it's how many users who quits versus new users gain. Use in the game. Yes, you're right. That's exactly how it is. So yeah, it would be churn, which is a classification example. We already discussed that. Okay, stock market is two kind of things, right? Stock market price prediction is two things. If you are trying to predict the price of the stock tomorrow, that's not classification, that's regression example. But if you're trying to predict if it'll go high or low, true or false, that's a classification algorithm. There's a huge difference. It's the same use case, but different kind of output. So yeah, I mean, you use a lot of them in collaboration as well. Spam email, regression or classification? Classification. Someone else should also speak. If you want to predict the price of oil, how about that row? How about you guys? Or the 5 of you, 3 of you, and 2 of you? If you want to predict the price of oil, would that be classification or regression? Yeah. Regression? Yeah, that would be regression because it's a continuous value. How about salary? If you want to predict salary? How about the 2 of you, the one behind the 3 guys? I'm sorry, what? Risk regression, correct. if you want to predict age, how about the two of you who are sitting closest to me? If you want to predict the age, would that be classification or regression? Like, yeah. I'm sorry, what? Well, kind of depends, right? If you want to predict by saying like, I am right now 39, and I want to say like, depends on the use case. So if I want to predict like how old would I be in 5 years, then that's like a regression use case. But if I want to say like, is this person 39 years old or not, that would be a classification. So yeah, I should have explained a bit. I should have asked a bit more what kind of use case it was. And the last one, which we already have discussed, is like gender. If you want to predict the gender, that could of course be like you have two data sets and you're like it's male or female, then that would be classification. Now, when you graphically draw it, it's a huge difference between regression models and classification models. Because you remember, like in the classification models, we have two discrete or four or n kind of data sets, and you had a hyperplane between them and they were divided, or you had something in between them, and they were always like classification of this data set is different from that one. But in regression, it's the opposite. They try to combine the data set and try to find like the unique point where they would meet. And that's the continuous value you find. So you have a huge scatter of data. You can have data all the way up to 160,000 and down to 20,000, right? What the model does is it tries to see where the data is condensed together. And when it finds the condensed part, it then kind of creates its own prediction based on where it's more heavily located. And that's the prediction you will get. So again, it depends on your historical values. If your historical values are all over the place, the prediction will also be all over the place. So try to find a clean data set, which can help you going forward. So I was asked a question in the chat, like, is one specific stock regression? Yeah, again, it depends on the use case. Are you trying to predict the price of the stock? Then that's a regression use case. But if you're trying to predict the stock will go up or down, it's like yes or no. Or if it's, yeah, if you should buy or sell, that's a classification use case. So yeah, okay, this is more important. So the difference between classification and regression algorithms. So the first and foremost, regression, the value should be continuous. In classification, it should be a discrete value, one value. Okay, then second, right, third, right, fourth. Fourth, I already showed you with the diagram. Fifth, we already discussed. Yeah, okay, but that's just you can read on your own. So let's talk about types of regression model. You have linear regression, logistic regression, polynomial regression, support vector regression, decision tree regression, random forest regression, ridge regression, lasso regression, and then you have a few more. But these are the ones which are commonly used or commonly known. But I mean, there are new ones coming all the time. So this list, yeah, can be updated. Let's talk about the first one, linear regression. So as the name says, linear, it's supposed to be a line. It's very similar to the diagram I showed you earlier. Like it takes a look at your data set and then tries to draw a line in your data set. So the way it works is that it tries to define the relationship between two points based on how well they are joined with each other. For example, the older a person gets, the relationship associated is that the wiser the person gets. And if you attend all the lectures, you will probably pass the exam, right? So you have an input variable and you have an output variable. Yeah, so a linear regression is straight line, right? And then you have a simple linear regression where you have a single input variable, and you have multiple linear regression where you have more than one input variables. But the output is supposed to be the same. You have to kind of predict like one output. Right. Again, a bit more of a theory over here. Like for a linear regression, what you do is for this kind of equation, what you're trying to predict is a salary, y is the salary, and x is the employee's age. So we want to, this is a very common use case where you want to predict how is age related with the amount of salary you will get. And so what some programmers want to do is that based on, if you provide them the age of a person, they'll then predict how much salary the person can make. And then coefficients are, of course, like, sorry. And the coefficients are the estimates of the unknown, right? That's something the model will calculate for you. Yeah. So when you try to predict it, what happens is that, again, it's very similar to what was going on with classification algorithms. And the thing is that the model has an idea of where the data points are. It tries to minimize the cost function. The cost function is common to all supervised machine learning models. And based on the cost function, it first tries to draw its line by saying, like, I think that this is the right value, but then it iterates and iterates and iterates until it finds the right value, which kind of unifies or kind of binds all of the data around it. Yeah. So these are the iterations we talk about. When you train a model, you have to iterate it until it finds the right value. I mean, it kind of does on its own. One second. Yeah. Okay. So the previous model we discussed, that was a linear regression, right? So we discussed that it should always be a straight line. But what if it's if your data is a bit more complex, right? So if your data is a bit more complex and you need more not a straight line in your data, then it's a polynomial regression you would use. You know, all this data, all these algorithms, the way they change is all based on the kind of data you have. That's why data is so important when it comes to AI development, because if your data is simple enough, you could just you either use logistic regression or some of the classification algorithm which works for you. If it's more complicated, you have more attributes which are interdependent, then either use support vector machines or use a polynomial regression. Look at your data and then see how the output should be. So in this kind of example, like if you were to use the same data set and you would have used linear regression on it, that's the output you would have received by linear regression. It's not bad. It's not bad. It's all right. But if you see, like, it's still deviating when it comes to the spots around 0.4 and 0.6. But when it comes to polynomial regression, that will give you a very right output based on how the data is scattered around. So every time you make a model, you have to plot the output. You have to see how the output was. That's how you plot the output, and that's how you know how your data was actually how the data and the output kind of felt at the right place. That's why it's used. That's why I'm stressing on the point that AI and machine learning development is done mostly in Python programming language, because Python language has out-of-the-box features which you can use to display your data. You can process your data and display it immediately. Other languages like Java, .NET, C#, they're not designed for data processing. They're designed for software development. Python is for data development only. To give you an example, in Router, we had like a file, a code which was written in SQL programming language. Do you know what SQL is? Have you worked with SQL? Okay, cool. Yeah, SQL is a very standard language, I think. That piece of code was 10,000 lines long. It was written over a lot of months. It was maintained in a very poor way. And you know, like when you work with SQL, it's not as easy to work with Java, because Java you can make classes, you can have objects, you have functions, you use them. With SQL, you just keep on writing down, and becomes one big file with 10,000 lines of code. And when we re-implemented it or recreated everything in Python, the code we got was 50 lines. That 10,000 was transformed to 50 lines only. And the reason is Python had a lot of functions which was doing all of the work we were doing in SQL. We were, like in SQL, we were loading the data from one table, then we had to write 50 lines of code to reload another set of data, then process it, then join it together, then transform it. And I mean, of course, we got a lot of memory out of bound exceptions, and we had to increase the memory. So the hardware which we were using to run that 10,000 line of code had at least 100 gigabit of RAM, just 100 GB of RAM to run that code. And when we moved it over to that 50 line of code, then the optimization was done by Python itself. And I mean, I think now it's running on a standard server which has 50 GB of RAM, and we never get like a memory out of bound exception. So for all kind of data operations, use Python programming language. That's the best one that's designed for that. For all kind of visualizations on your data, use Python language. For all kind of software development, use Java, C#, or anything else you want to use. They're good with that, not with Python. And if you want to do AI, a lot of machine development is actually supported by Java, .NET as well. But most programmers don't use them because it's harder to do it with those languages. It's easier to just look at your output directly with Python. All right. Where are we now? Oh, that's interesting. This is actually the end of the slide. Okay. I guess that was it. And we are kind of free pretty early. Okay, do you mind if we finish a bit early? I mean, I do have another machine learning course, but I mean, I could, that's not really planned. I thought this might take a longer time, but okay, we do have a lab today. Thiago, the lab was at the machine learning lab, right? Yeah. So the lab today is regarding how you can actually implement a machine learning algorithm. Which algorithm was it again? Sorry? Linear regression. Yeah. Based on classification or regression? Regression. Okay. So yeah, take a look at the lab. This is a supervised machine learning lab in which you use a linear regression algorithm. Yeah. So now we are done with supervised machine learning. The next class we'll talk about non-supervised machine learning. That will go really fast. I think now we have only 2 machine learning classes more. Just cover the basics. The next assignment will also be based on you submitting a machine learning application, either supervised or non-supervised. We'll talk about that. So that will be the most difficult part, and then we'll be done. Like we have another assignment, but that's more of an easy assignment to work with. The next class, the next week, I don't think we have a class, do we? Do you have like a week off next week? It's like autumn vacation? No? Or you are coming? Can anyone answer? Okay. All right. Are all of you coming to classes? Is there anyone who's okay? You know what? I should actually ask the admin and come back to you. So I'll inform everyone. But for now, what I have been informed is the next class is off. So there should not be any class in the coming week. If admin tells me that there should be a class, then I'll just send you an email and tell you about it. All right. Thank you so much. I'll just take the questions there.